Last summer, in the middle of a heat wave, my room hit 35 degrees Celsius. At midnight, the fan was on full speed, but it wasn't cooling anything. It was just pushing hot air from one corner of the room to the other. And the air conditioner? It worked. But every hour it ran, I could almost hear my electricity bill climbing. And that's when I realized something strange. We've built entire systems, expensive, energy-hungry, maintenance-heavy systems, just to make air a few degrees cooler. But what if that's the wrong approach? What if cooling a space doesn't require more power, but better design? Because here's the part no one talks about. For thousands of years, people lived in climates far hotter than ours, without electricity, and still managed to keep their homes cool enough to survive and even sleep comfortably. So the real question isn't, how do we cool a room? The real question is, why are we solving this problem in the most energy-intensive way possible when simpler systems already exist? In this video, I'm going to show you a forgotten cooling system that costs about $5, takes less than 20 minutes to build, and runs without electricity. But more importantly, I'll show you why it works, when it works, and how to turn it from a simple trick into a real system. This isn't a hack. This is something we forgot. Before we build anything, you need to understand one simple idea, because once you see it, everything else makes sense instantly. Cooling doesn't actually come from machines, it comes from energy changing form. When water turns from liquid into vapor, it needs energy to do that, and it pulls that energy, heat, from the air around it. That's evaporative cooling. It's the same reason your skin cools down when sweat evaporates. Your body isn't creating cold, it's releasing heat through a phase change. Now here's where it gets interesting. The speed of that process depends on three things: temperature, humidity, and airflow. Hot air holds more energy, so evaporation happens faster. Dry air can absorb more moisture, so the cooling effect increases. And moving air continuously replaces saturated air, allowing the cycle to keep going. Modern air conditioning systems force this process using compressors and refrigerants. But at its core, they're doing the same thing, moving heat from one place to another. The difference is this: one system consumes energy to control the environment. The other uses the environment itself as the energy source. And once you understand that, you stop asking, how do I add more power? You start asking, how do I design the system so power isn't needed at all? Now here's the piece that turns a simple idea into a powerful system: activated charcoal. On its own, water evaporates slowly because its surface area is limited. A flat tray of water only exposes a thin layer to the air. That means limited contact and limited cooling. Activated charcoal changes that completely. Just 1 gram of activated charcoal has a surface area of up to 1,500 square meters. That's not a typo. It's because the material is filled with millions of microscopic pores, tiny channels and cavities that trap water across an enormous internal surface. When you soak charcoal, you're not just wetting the outside. You're loading water into a vast internal structure. So instead of evaporation happening on a flat surface, it happens across millions of microsurfaces at the same time. The result is a massive increase in evaporation rate, and that means more heat is pulled out of the air faster. But there's a second effect most people miss. Activated charcoal doesn't just hold water. It also binds to airborne particles, odors, volatile compounds, even certain bacteria. So as air passes through it, you're not only cooling the air, you're cleaning it. At that point, this stops being a material. It becomes a system multiplier. Long before electricity, long before compressors and refrigerants, entire cities were already solving the problem of heat, using nothing but air, water, and intelligent design. In ancient Persia, engineers developed what are known as wind towers, or badgir. These structures were built directly into homes and public buildings, rising above rooftops to capture even the slightest breeze. But the real innovation wasn't just catching the wind, it was what they did with it. Air was channeled down through vertical shafts and forced across damp materials, often clay surfaces or charcoal, before entering the living space. As the air passed through these wet layers, evaporation occurred, pulling heat out of the airflow before it ever reached the room. The result wasn't just ventilation, it was passive cooling. In places like Yazd, where summer temperatures regularly exceed 40 Celsius, these systems maintained indoor environments significantly cooler, often by 8 to 12 degrees, without a single watt of electricity. And here's the key insight: they didn't fight the environment, they designed with it. Instead of generating cold air, they controlled how heat moved, guiding airflow, maximizing contact, and letting physics do the work. What we're building today isn't new. It's a simplified version of a system that already proved it works. Now let's build this, but more importantly, let's build it the right way, because most people will turn this into a hack and then wonder why it doesn't work. The materials are simple: activated charcoal, a shallow tray, water, and a source of airflow. That's it. But the performance doesn't come from the materials alone. It comes from how you arrange them. Start by spreading the charcoal in a layer about 3 to 5 centimeters deep. Add water until it's fully saturated, like a wet sponge, not flooded, not dripping. What you're creating here is a high-surface, moisture-loaded medium. Now here's where most people get it wrong. They place it in the middle of the room, and nothing happens. Because this system doesn't cool air randomly. It cools air as it moves through it. So placement is everything. You want this tray positioned exactly where air enters your space: a window, a doorway, or directly in front of a fan. That way, every bit of incoming air is forced through the charcoal before reaching you. At that point, you're no longer using an object. You're shaping a flow. And once airflow is controlled, the system starts working the way it was designed to. A system only becomes useful when it works beyond a single example. So the question is, how do you scale this? The answer isn't to make one unit bigger. It's to think in terms of flow, surface area, and coverage. For a small space, a bedroom, a dorm, a camper van, one tray placed at the primary air intake can make a noticeable difference. But as the space increases, the limiting factor isn't the material. It's how much air is actually passing through it. So instead of building one large setup, you create multiple smaller units and place them at key intake points: windows, doors, ventilation gaps, anywhere air naturally enters the space. Now you're not cooling a spot. You're conditioning the entire airflow system. For larger environments like greenhouses, barns, or animal enclosures, you can take this further. Build a shallow frame, fill it with charcoal, and mount it directly into the airflow path. Every incoming breeze is filtered and cooled before it spreads through the structure. The principle stays the same: increase surface area, increase air contact, increase exposure time. When those three variables scale together, the system scales with them. And that's when it stops being a trick and becomes infrastructure. Now let's be honest, because this is where most videos lose credibility. This system works, but it doesn't work everywhere the same way. Evaporative cooling depends heavily on humidity. The drier the air, the more moisture it can absorb, and the stronger the cooling effect. In dry climates, this system can feel surprisingly powerful, dropping temperatures by several degrees and making a room genuinely more comfortable. But in humid environments, the air is already holding a lot of moisture. That slows down evaporation, which means less heat is removed from the air. The system still works, but the effect is reduced. Instead of dramatic drops, you might see a modest improvement, just enough to take the edge off the heat. There are also practical limits. This won't replace a full air conditioning system in extreme conditions. It requires airflow to function, and it needs maintenance, keeping the charcoal damp, refreshing it over time, and placing it correctly. But here's the important distinction. A system doesn't need to be perfect to be valuable. It just needs to be predictable. And once you understand when this works and when it doesn't, you stop guessing and start using it with intention. So if a system like this is so simple, so cheap, and has been working for thousands of years, why did we stop using it? The answer isn't that it stopped working. It's that our priorities changed. Modern systems are built around convenience, control, and consistency. You flip a switch, and no matter the conditions outside, you get the same result. But that convenience comes at a cost: energy consumption, infrastructure, maintenance, and long-term dependency. What we lost along the way is something more subtle. We stopped designing with the environment and started trying to override it. Systems like air conditioning force a result using energy. Systems like this one achieve a result by aligning with natural processes: airflow, evaporation, material properties. One scales with electricity, the other scales with understanding. And that shift matters more than it seems, because once you start seeing problems this way, you realize there are entire categories of solutions that don't require more power, just better design. This isn't really about cooling a room. It's about remembering that some of the most effective systems don't plug into the wall. They plug into how the world already works. And once you see that, you can't unsee it.